There we go.
Okay, so we stay on for now, and then.
Yes, I think we should be live. So, hi everyone. My name is Ilias. Introducing the speakers for the parallel computing session. So, let's start with Mark Hornick, who will tell us about exploiting data parallelism for our scalability. Mark, the floor is yours.
Great. Well, thank you very much. Great to be here. And I'm just going to share a video and I'll be on for questions afterwards. Welcome to this session on exploiting data parallelism for R scalability. In this session, we look at achieving data parallelism in R and how Oracle Machine Learning for R makes it easy to do this with database data, while simplifying deployment in applications. My name is Mark Hornick with Oracle Machine Learning Product Management. To set the stage for talking about parallelism, the goal is to improve performance by running multiple computations concurrently. Like most things, achieving parallelism can range from simple to complex. Typically on the complex side is individual algorithm parallelism. Many algorithms are implemented with serial processing in mind. And to gain the benefits of parallelism, some require significant redesign, and others, by their very nature, simply can't be parallelized. Now, toward the other end of the spectrum is data parallelism, where the basic algorithm is run on data in parallel using multiple threads or processes on data partitions. So let's relate that to R packages. Some operate sequentially, so there's no parallelism enabled by the package. Some may use, for example, matrix algebra functions and can leverage implicit parallelism via optimized math libraries, like Intel's MKL. So there's no algorithm redesign needed. Still, other packages are designed with parallelism in mind, but may rely on specific parallel packages and infrastructure. Now, while achieving algorithm parallelism may require a package redesign, data parallelism techniques can be applied to any of these. So for a moment, though, let's talk about scalability and performance. One of the first considerations for scalability is data movement. Moving data, especially large volume data, can be problematic. There's the time it takes to move it into memory or local disk, whether from a flat file or a database. And this can be costly as bits travel across the wire, especially if cloud vendors charge for data movement. And we also need to consider data backup, recovery, and security. Ideally, we could leave data where it lives and perform processing locally. Let's discuss another scalability concern, available memory. Most R packages expect data to fit in memory. For example, when filtering or transforming data, or building or using machine learning models. Of course, if the data doesn't fit in memory with enough left over for processing, we need a different approach. With data parallelism, we achieve scalability by partitioning data and processing each chunk. If the data resides in a single file or table, we first need to partition that data, which allows us to process it sequentially. So we've addressed scalability, but what about performance? To achieve performance, we introduce parallelism. And if we spawn multiple R engines, we can expect to see elapsed time reduced significantly, perhaps by as much as a factor of the number of R engines used. This type of approach is often referred to as embarrassingly parallel, since it's so easy to implement. So what are some use cases that can benefit from data parallelism? Well, perhaps the most obvious one is scoring data at scale, which is inherently an embarrassingly parallel problem. Other partition data computations include computing statistics or generating plots like per customer or per region. Model building too can benefit by using different data subsets to create ensembles. And Monte Carlo simulations may be run on data that is randomly generated or selected. So let's take a specific example of how we might use data parallelism to make predictions using R's parallel or for each packages. To start, we'll build a naive Bayes model to predict species. We're using the familiar iris dataset. And after connecting to the database and pulling the data into memory, we define our function to build the model and save it to disk. Let's start by using MCLApply from the Parallel package for scoring data. While we're using the iris dataset with only 150 rows and 5 columns, which easily fit in memory, consider the scalability implications at each stage if we have 100 million rows to score. Now connect to the database and pull the data into memory. And to enable data parallelism, partition it in some number of groups. Here we chose 15 with 10 rows in each. On larger datasets, imagine each partition consisting of many thousands of rows, but this depends in part on the cost of producing each scores and the available memory. Then we load our model from disk and invoke MCLApply with our partition data and scoring function. To get maximum parallelism, let's choose 15 cores to match the number of partitions. Now, since the result comes back as a list, we first R-bind the results before writing those scores to a database table, although we could iterate over the list of data frames to insert them in the table incrementally. Now, finally, we compute a confusion matrix off the actual and predicted values. Of course, all of this data needs to be present in the local R environment for this to work. We can do something similar using the forEach package, but here we first explicitly make and then register the cluster, and when finished, stop the cluster to free up resources. So what scalability concerns do we have with this approach? Well, we need to pull the data from the database to the client and then partition it. The partition data could actually consume significantly more memory than the original data, so we need to factor this into any solution. Since our model is stored in a flat file, we need to ensure our production process has access. We also need to factor in backup, recovery, and security for our data, model, and scripts. All the processing occurs on the client machine, so it needs to be sized to meet the need. And lastly, the result is returned as a list of data frames that need to be R-bound together. And if this itself is a large result, additional memory considerations may come into play. We address these concerns with Oracle Machine Learning for R leveraging the database as a high-performance compute engine. OML for R avoids pulling data to the client R engine and consuming client memory. The database automatically spawns and manages R engines with the benefit of system-supported data parallelism. And we can store R objects and user-defined functions in the database, getting the benefit of database-level security, backup, and recovery, along with access control. As we'll see, database tables are accessed through data frame proxy objects with overloaded functions that produce SQL transparently behind the scenes. And this includes overloaded dplyr functions for manipulating data in the database. Part of the OML for R capabilities are in-database machine learning algorithms that are exposed through an R API using the R formula. And these algorithms are designed for parallelism and scalability. All processing for model building and scoring occurs directly in the database using these algorithms. Here's the code that builds the model, storing it in the database, while having the database spawn and manage the R engine to process it. Our UDF builds a model to predict species using a data frame passed as the first argument and saves the model to the database in what we call a data store using ore.save. The return value is simply the Boolean true. Next, connect to the database, create our UDF in the script repository, and get a proxy object to the iris table. Then we invoke ORE table apply, providing the proxy object iris, the name of the function in the script repository, the name of the data store under which we'd like to store this model, and to automatically connect to the database from the spawned R engine to access the data store. The database environment spawns an R engine, loads the UDF and iris data from the database, and when finished, we have our model saved in the database and the R engine is released. We can invoke our model building UDF from SQL as well, say to allow our application to build this model. Using a select statement with the RQTableEval function, we specify the source data using a SQL query. In this case, select star from iris. As in the previous example, we specify the function arguments. Indicate that the result should be returned as an XML string. Recall the result is just returning true. and give the name of our UDF just created in the script repository. With the model created and stored in the database, let's define a function that uses that model to make predictions. As before, ORE script create stores the UDF in the database script repository. We can also store our UDF using PL SQL with the function rq script create. And this allows DBAs or SQL users to receive UDFs from our developers to deploy them themselves, perhaps in secure production environments. So now let's use OML for R to get data parallel behavior using our scoring UDF. After getting a proxy object to the iris table, we provide it to ORE row apply, along with the function in the script repository. And that we want 10 rows to be processed at a time, do this in parallel using 15 R engines. The fun.value parameter specifies the resulting data frame structure, so it can automatically create a single result, as opposed to a list of partial results. Invoking row apply causes the database to spawn the R engine, load the UDF and data partition into each, and collect the results, which are presented as a single ORE frame proxy object. And this is important since results themselves can be large, and we don't want to pull results to the client unnecessarily. Next, we create the table batch scores and use the overloaded table function to compute the confusion matrix in the database on the batch scores proxy object. Note that only the confusion matrix itself is returned to the client without the need to load large volume data to the client R engine. Here's the corresponding SQL invocation using rq-row-eval. You'll see some familiar parameters from the previous example. We have the data iris with a parallel hint to indicate that we want 15 R engines. We have the parameter list, the result structure, the number of rows to feed in each invocation, and the name of the UDF in the script repository. So let's see a brief demonstration of OML for R embedded execution. So we're looking at RStudio, and we're going to run our script to explore exploiting data parallelism using Oracle Machine Learning for R. So the first thing that we'll do is to load the ORE packages, and then we'll connect to the database. And what this does is to create a set of proxy objects that we can now use that correspond to database tables. We'll look that we have the iris proxy object. We see that it's of type ORE frame, and we can see the first few rows of that data that have been retrieved from the database. Next, we'll define our build NB model function. We'll create that script in the script repository, giving it the same name as the function. So from here, we invoke ORE table apply. So what's just happened? We have spawned the R engine, loaded the function and data, built the model, and stored it in the data store. And so we have our data store, naive Bayes model iris species. We can see its size and creation date. And if we look at the contents of that, we see that we have an object that is named mod, and the class is naive Bayes. So now let's score using this model. So our scoring function is going to again load the library, load the data store that contains our model. We're going to use that model to make predictions and then return the actual and predicted value. So we'll create that script in the script repository, and now we'll use ORE row apply to invoke that. We're going to pass again our iris data set. Our function name is score NB model. We have the data store name where we're going to be loading that model from, that we need to connect back to the database to access the data store, and that we want 10 rows, 15 R engines, and this is what the result is going to look like. So let's run that. And we see the result of our predicted class is an ORE frame as well. Let's now create the table batch scores. So we're going to first drop that table and create that table. And it's at this point where we're actually trying to access the results that this is being processed and the table is created. Now let's look at the first few rows in our batch score proxy object, and we see some of the results. But we can use that same ORE frame to use the overloaded table function to give us our confusion matrix. Well, let's take a look at Sql Developer now to show how we can do the same thing from SQL. In this case, we're going to use RQTableEval. We have our cursor where we're selecting star from the iris table, passing in our arguments. We have an XML string, our build NB model as the function that we're going to invoke. So let's just run this. And this is showing that we got back true. Okay, well, we've just built our model from SQL using the RQTableEval function, passing in the iris data. But as we mentioned, you can store your scripts in the script repository from SQL as well. And here we're going to store again the score NB model function in the database using the SQL API. So we've now stored that in the script repository. We can see that this script exists in the script repository also from SQL. Let's drop the table batch scores and create it dynamically using RQ-row-eval. And we're going to do a CTAS, the create table as select, using this query that we showed in the slides. And from here, we can use that table that we've just created to get our confusion matrix directly as a SQL query. So that ends our script with the Sql Developer. So far, we've seen the table eval and row eval functions in our examples, but there are others to support additional use cases. For more information, here are a few resources, including blogs, additional code examples, and documentation. So thanks for joining this session, and I'm happy to take any questions.
Thank you, Mark, for that. Are there any questions for Mark? I don't currently see anything in the chat or the Q&A, but let's maybe give it a minute.
Okay. One question I often get is this available for existing Oracle database customers? And the answer is, yeah, if you have an Oracle database, you can download OML for R and you can install it and use it as part of your Oracle database license. So it's free, basically.
That's good to know. I think since there are no questions at the moment, let's move on to the next speaker and we can come back if there's any questions for Mark at the end. So unfortunately, one of the speakers is not here, so we'll move on to Piri Kantani, who is here to talk to us about one second. Experiences from C high-performance computing environments by handling synthetic national identification numbers. So, Piri, the floor is yours.
Thank you. I will just share my screen and then we can start. Yeah, you're probably seeing my screen just fine. Let's see. Yeah.
I don't think we can see your screen yet. Sorry.
So do you see nothing or?
I just see the video.
Right. I think I will have to permissions for Chrome and I have to restart it. I'm sorry, but I will be back.
No worries. In the meantime, Mark, I think there's a couple of questions in the Q&A. Do you want to come back? So the first question is R enabled by default in Oracle Enterprise? I can't hear you.
Sorry. On the Oracle database, you need to install the R engine on the database server side, and then also install the OML server components on that. So let's say that you had a multi-node cluster. We often have Exadata as a machine. You would install R on each of the nodes on that machine, and then you would also install the server components. And if you had additional R packages that you'd like to use with the embedded execution, you could install those there as well. So that's how you would approach that. And
Great.
I see it's
And
possible to
question.
show the links again. I can post those in the Q&A, so I will grab those and put those there.
Maybe in the chat, so they don't show up as another question.
Chat is fine. I'll put them there then.
All right, Piri?
Yes, hopefully now it should be working.
Yes. Perfect.
Yes, looking good. Perfect. So, yes, good evening, everyone from Europe, Finland. I'm Pyry Kantanen. I'm a research assistant at University of Turku at this ROpenGov project. And Leo Lahti is my supervisor. And I'm going to talk today briefly some very basic examples of our experiences in working in the CSC, high performance computing environment. And today's example is handling synthetic national identification numbers. So first of all, I would like to start by telling what CSC is, since I think probably very few here know what it's about. So CSC is a Finnish state special organization or a special company that is owned by the state and the Finnish higher education institutions, meaning universities and universities of applied sciences. What CSC does is basically provide computing resources for academic research, as well as provides training to the users. And also they sell some computing time to private parties as well. And what is important here is that they offer several different supercomputers for academic research. The most general one is called Puhti. That's a Finnish word. And in this demonstration, I have used Puhti environments. Puhti has several heterogeneous CPU nodes with different memory sizes, and also has a separate GPU partition for more parallel problems. Then there is Mahti, which is more homogeneous with emphasis for more massively parallel jobs that require at minimum 128 CPU cores. Also, there is Quasi for quantum machine learning and Lumi, which is one of the 3 European pre-exascale supercomputers just recently introduced. So this is from training slides from CSC, and the event was about geospatial datasets in R. So it has this emphasis on the geography and environmental sciences. But as you probably would have guessed anyway, the most resource demanding disciplines are physical sciences and biological sciences and medical and health sciences. I come from a scientific background, so you might notice that there is no social science to be seen on this chart. But our group, me and Leo, and some other people who are interested in computational humanities and computational social sciences would like to change this and start to do more in regards to computational social science. So this is just a motivational chart in that sense. Also, yeah, some basic information about national identification numbers. So good national identification numbers are immutable and unique in the sense that they make it possible to identify individuals, natural persons in a given area over their life course and also afterwards. And national identification numbers are a subset of identification codes that can be given to almost anything from books and companies and chemicals. Different things have codes that make them easy to discern from similar things. Of course, from the government's perspective, these national identification numbers are very convenient because they enable, for example, register-based censuses and other official statistics production, taxation and payment of pensions and so on. From a private business perspective, using these codes enable checking credit ratings on individual persons before giving loans or installment payments, and also for individual people, using these codes makes it possible to check what kind of information has been stored about you in different registers that are quite numerous nowadays. And we have just recently submitted a paper to our journal about Finnish and Swedish national identification numbers. Finnish and Swedish national identification numbers are quite similar with each other, and also similar to other Nordic national identification numbers. And all of these numbers have some information, additional information embedded in them. For example, the birth date of the individual, sex as a binary classification, and some check digits and control characters that make it easy to detect input errors that were very common if these are manually inputted in some forms. You can read the draft if you're interested more about these. And here is just an example of the Finnish national identification numbers with 11 characters, the days, years, and months of the birth date with a century marker determining the century in which the individual was born, and the three number individual number or a serial number, and a check digit. And we can see here that for each day of the year, there is exactly 898 valid individual numbers. So in a sense, 499 valid numbers for males and females. So the number pool is limited, but has been sufficient so far. And it makes this generating these numbers, when we think about when the first people have been assigned these numbers, it makes the pool of numbers limited. So it's not going to be in the billions, but rather in the tens of millions, which limits this problem that we have here. And yeah, also some basic information about running R in CSC Puhti. Basically, it can be run on the Singularity containers that run on CentOS Linux. And there are 3 different versions of as of now. The most recent being 4.1.1, which I have been using. And the containers that contain commonly used R packages pre-installed in read-only memory but in project-specific instances, user packages can be installed manually into a separate directory, which I have done in this case by installing, of course, the hetu package, which I have been using. So, as it was said also in the last presentation, some basic things about parallel computing in R. Basically, it can be divided into multiprocessing and multithreading. And in multiprocessing, multiple copies of R are launched, and there are two different cluster types, and the cluster types refer to how independent R processes communicate with one another. In the fork clusters, the currently running R process is copied and allocated to a new core, whereas in the socket cluster, an entirely new R process is allocated to each core, and each process starts with an empty environment. These fork clusters are limited to POSIX systems such as Linux and macOS, whereas these socket clusters are also supported by Windows. But of course, in the CSC environment, it is run on Linux, so we don't have to, in this case, pay attention to Windows compatibility. But of course, it's nice to do that in general. And multithreading is another paradigm that R can be configured to use multiple cores via multithreading, but we will not use the multithreading paradigm today. So, short basics of the high-performance computing. Basically, supercomputers operate on multiple nodes at a time, and CPU, in one node there is a CPU and memory, so it's basically a small computer in itself. And these nodes are connected together with a fast network, with an interconnect. And when we talk about parallel computing, we must also discuss parallel scaling, where we compare the execution time of solving these mathematical equations in serial and solving these mathematical computers in parallel. And we get this score, which basically determines whether the performance scales well or not. And basically, there are different things such as parallel overheads, extra operations, communication and synchronization costs, load imbalance, and serial parts in the problem that limit the ideal world of parallel computation. And here is a nice graph that illustrates basically how in real world adding more cores does not solve the problem more faster. And we can also see a tipping point here where adding more cores actually makes it solve the problem a bit slower compared to having the optimal amount of cores. And here is another from Imre Gera's blog, another picture which basically just shows that the overhead must always be taken into account when comparing these task speeds. Well, in the for each package vignette, parallel computing is basically defined as doing three things: splitting the problem into pieces, executing the pieces in parallel, and combining the results back together. And while using the hetu package, we determined that the slowest function was the random generator that creates these synthetic national identification numbers. And since we know that national identification numbers are not dependent on each other. They are suitable for being generated in parallel. And for example, by dividing the date ranges evenly between cores, these numbers can be generated simultaneously without fear of duplicates. Here is a very trivial solution to this problem, just simply using for each. And if the problem was more complicated, we would have to use, of course, more complicated solving methods. And but in this case, this is sufficient. Our interest in the using of HPC resources and in general running R in the cloud is related basically to promoting the use of R in social sciences and promoting the use of these methods in general in social sciences. And especially when it comes to handling datasets, registered datasets that have national identification numbers. National identification numbers themselves are sensitive data, but they're not the most sensitive data that is handled in social scientific research. And these sensitive datasets have to be handled in remote, secure environments. And by using R in social scientific research, we think that it would speed up the the process of developing new methods in social sciences instead of the current paradigm of using these commercial solutions from different vendors, which I'm not going to mention here, but you might guess what these other statistics program vendors are. And also, when handling sensitive datasets, it's of course, one solution is always to buy a newer and better and faster computer, but with sensitive datasets, you can't do that because you will not get the dataset in your own computer. You will have to run it in the cloud. So developing these types of initially simple methods like I just showed you here, but in the future, more complicated methods and demos, we will want to promote this type of using R in social sciences. But I thank you for your time, and I have links to our OpenGov website and GitHub repository and some basic information about CSC, which is or should be accessible to academics around the world, at least if you collaborate with Finnish scientists. Thank you for your time, and I look forward to your questions.
Thank you very much, Peter. Let's wait a minute or so for questions because I think there's a bit of a delay.
Can I ask a question?
Of course.
Yeah. So I saw your comment about sensitive data, and that's super important. And I know some people solve it by having dedicated computers or servers that you can run sensitive data on, and others don't have sensitive data. What's your setup in this compute environment? Do you trust the whole compute environment, or do you have to run things on certain compute nodes, for instance?
Yes, it's a separated environment for sensitive data, and I personally have no experience on using these sensitive data environments, but I have understood that they are not usually as powerful as these HPC setups that are used, and they're actually can be all quite slow in reality. But I hope in the future that they will gain similar resources also there. But of course, there are maybe some security considerations that limit these types of capabilities that I'm not even aware of, because I'm not an expert in that field at all, building these secure systems. But yeah, that's, I think, the current solution, at least here in Finland, to have these separate.
I've seen and heard of different solutions, and some say, I mean, you get much more extra overhead if they need to run everything encrypted. Nothing can be stored on disk unencrypted. Can only be run one user per compute node, because other processes shouldn't be able to peak. And then others are more relaxed and say it's enough to run it in a container on a shared environment and things like that. So it's I don't know much either, but it's a very interesting topic, and it's important for some people out there, especially in life sciences and things like that.
Yes, I'm in the life sciences field, and I've heard recently about people trying to develop algorithms that work directly on encrypted data to try and minimize the overheads.
Yeah, there's a lot of interesting research on that too. Yeah.
Right. I don't see anything on the Q&A, but if there is anything, we can pick it up at the end.
Sure.
But thank you very much, Fir. And I'd like to introduce our next speaker, Hein Bengtsson. Sorry.
Oh, that's good.
Who is going to talk us about Futureverse and profile parallel code. So the floor is yours.
Thank you. Hi, everyone. What I'm actually going to do now, I have prepared some polls. I'm launching them all at once, and I will see the feedback. I'm asking if, about our parallelization, what your operating system is, your R environment. There should be 4 polls coming up. See if I have them. Yep, they should be all there. So we can look into later. That's always fun to know who's attending here. I'm going to share my screen. And so I might have the same problem with as previous speaker. I'm really sorry about that. This did work for me on my tutorial on Monday, so I am having to join through another web browser. This is very weird.
Not a problem. It'll give people time to answer the polls.
Yeah, it's not meant to be easy, is it?
I wonder if the Q&A chat was directed to me, preventing writing sensitive data to the disk.
Yes, you can answer that if you'd like.
Yeah, sure. I think now we have time when juggling the browser. Yes, in the CSC HPC environment, at least, it's not restricted on writing data to the disk. Although I'm not sure if this refers to these secure environments where I think, yeah, at least in Finland, they usually are configured so that the user can't write any own scripts in the environment, or if they can, they basically write the scripts themselves, but they can't take them out of the system except by writing them again by hand. And the results are also these anonymized and summarized results and not the raw data. So they go through some information official before they can be taken away out of the system. But I hope that answered your question.
Okay, I think we got success. I hope.
Yes, we can see now.
Thank you. Sorry about that. Every day there's a new bug fix going on. Okay, so I am going to present to you the Futureverse framework, and specifically today about how work on profiling parallel code and finding bottlenecks. I'm going to give a small introduction to Futureverse for those who are not aware of it, but the main goal is like this question: where can we improve? And that means like where can we improve the Futureverse package itself, but also developers using it if they're finding bottlenecks. So this is a work that we wanted to start being a feature request for a very long time, and this work has now started and it's going to happen here. Okay, so Futureverse, what is it? It's an ecosystem for parallel and distributed computing in R. It started out as a core package, and this core package is called Future. The goal is for that to handle everything, do all the fancy orchestration you don't have to worry about. And it's also providing a unified experience throughout the whole Futureverse ecosystem. It will always be a minimal package, trying to make it smaller and smaller. It's not going to gain extra functions, maybe extra features, but not functions. This package and its core API allows us to build up other higher level parallelization frameworks like MapReduce packages and APIs. For instance, the Future Apply package, the FUR from Davis Vaughan, the DoFuture adapter towards the For Each package, which then also allow you to use it for the applier and biasing parallel and other things that rely on For Each. The core allows you to plug in a new parallel backends, and there's a well-defined API for that. So that means we have existing parallel backends that we know on from the parallel package, and a package called Parallely, which enhances that. That allows you to run locally, remotely, through MPI in the cloud. The other backends built on top of the Collar is also local parallelization. There is the Batch Tool package, and we have a backend for that allows you to use a job scheduler and high performance compute cluster to do your parallelization and distributed processing. And I also said more to come, because there are more to come, and it's designed so anyone can add new backends, and your code will just work with those new backends as well. There is also, I just want to mention it briefly, there is a package called Progressor that allows us to do near live progress updates also when we run in parallel and remotely, etc. And that one is in bridging towards existing, like the CLI CLI package, and will come soon, the Progress package and other progress reporting frameworks in R. Okay, so a brief introduction to this in detail. So there is the Future package at the core. It provides a simple unifying solution for parallel APIs. It's designed so you can write your code once and it can run anywhere. 100% cross-platform, so Linux, Mac, Windows, Solaris, whatever. It's easy to install, small. It's very well tested, got lots of CPU mileage. I've used it for like very large genomic sequence processing on compute clusters. It's used in production throughout the world. It's designed so things should just work. So it's like minimal friction for you when you use it. Correctness and reproducibility is highest priorities, because otherwise those things can be tricky when you do parallel processing. And we have a web page, futureverse.org, that collects everything and links to the different packages. And by the way, I didn't say that on my intro slide. The talks will be available there soon after this presentation, this talk. So the package was released back in 2015, so actually 7 years ago on Sunday. Since then, the uptake been very rapid, more than I expected. There are now more than 200 packages on CRAN that rely on the future package. It's the top 1% most downloaded package any week. The future apply package and FUR was released a little bit later, and they also see a great uptake on usage. So that's nice to know that people find it useful, and it gets a lot of testing throughout this usage too. So some quick examples how you parallelize with futures. You can imagine this very simple case on the top here, sequential processing. We have a variable x with value 7. We pass it to a slow function, and that function takes a minute to do its calculation before we assign the results to y. Then we have another function that is also slow, but not as slow. It takes half a minute, and we get the value to z variable. So how can we do this in parallel? There are different ways, but this is the most simple way, basic one, with the future framework. We load the package. We instruct the future framework. We want to use multiple sessions on the local machine. And then when we take the slow function here, we just say we want to evaluate that within a future. And that means we don't care about the result right now, but sometimes in the future we want to know the results. So this function takes the expression, wraps it up, sends it to the background worker, and gives back a handle to it, which I call f here. And that returns immediately, basically. So now we're free to do other things in our main R session. And in this case, we can actually use the main R session to call the another function here, which takes half a minute to finish. So now these two run in parallel. We then say, okay, now we're interested in the value of this future. So we call the function value. And if it's not done, it will wait until it's done, but it will take a minute, half a minute. So this one takes half a minute, and then we have to wait another half a minute to the original. So all in all, both these finish in 1 minute instead of 1.5. So that's a very simplest way of parallelization in R. And all parallelization frameworks in R has something like this under the hood. But the most common one is to use some kind of map reduce. And so if you consider the base R apply function, so for instance, here we have the list apply or the L apply. So if you want to apply this slow function to 20 different values, it will take 20 minutes because each call takes 1 minute. So if we're using the future framework, we can use the future.apply package, which implements all the base R apply functions. And we can use those. And then we instruct it to run in parallel in the background. And all you have to do is to take your original lapply and replace it with a future underscore lapply, nothing else. And now this will run in parallel. And on this example, I used it on a 4-core laptop. So it will have 4 background workers. So that means it will run 4 times faster. So you finish in 5 minutes. If you work in the tidyverse, you might use the per, and then there is a map function there that you can use. And that works very similar to lapply, and that will take 20 minutes, of course. But you can use the fur package, do very similar thing, and replace it with future underscore map. So that's will take 5 minutes. So if you look here, a key thing and design feature with the future framework is we separate how to parallelize, that's the plan here, with the what to parallelize. So when you program, you just decide what to parallelize, and then we leave it to the end user to decide how to parallelize, because the end user is the person who knows the best what computational resources they have. So some might say, I want to run your code sequentially, or I want to use all the cores on my machine, or I want to use 2 parallel workers on my local machine. Another user might have access to both local and remote machines. As long as you have SSH access to these machines and they have R installed, you can use this approach. And so here is an example where one worker is running on a local Raspberry Pi, another one is running on a remote machine. So this was set up 2 parallel workers. Some other users might have access to large high-performance compute clusters with thousands of workers and many hundreds of nodes, and each node has many hundred cores. So they might want to submit their evaluation or the futures to the job schedulers. And this is through the batch tool package. And this is an example, batch tool _slurm. There's a job scheduler called Slurm. There are others called Torque or Sun Grid Engine and so on. So it's up to the user to decide. Okay, so the futures are unique in one way if you compare to other parallel frameworks. First of all, it's identified globals and exports them automatically. I know for each does that too, but it doesn't go all the way in, and there's work of actually harmonizing that with the futures. But basically, there are things that needs to be sent over to the parallel workers so they can do like functions and things like that. It also relays output and conditions that are signaled on the parallel workers. This is unique. So, of course, errors are handled by most parallel frameworks. Here, errors are reflected identically back to your own on the main R session, but also warnings, messages, and standard output. And I'm not aware of any other framework that does this. And this is all to minimize the surprise from going from sequential to parallel processing. It has a built-in statistical sound random number generations. Can do near live progress updates also from remote workers. And the goal here, and this is a little bit important, understanding the design and why we don't add features, is like you as a developer shouldn't think about parallel workers. You should just think about what are expressions to parallelize. Okay, so what about profiling here? This is something we wanted to do for a long time, and we've been manually trying to do this, but now there is a framework for doing that with the future framework. So the point here is like to build up a journalistic system to log events, like creating futures, launching them, measuring evaluation, and gathering results. For now, we're only doing timing information because that's the easiest. Memory is tricky, especially tricky across platforms, but hopefully we can get to that, to profile memory too. It's designed to be working with all parallel backends out of the box. Near zero overhead is critical, so if we don't profile, it shouldn't cost anything. Data should be available as raw data. So whoever can analyze this can do it, but there should also be built-in textual graphical presentations. So here is an example. Let's look at a sequential future. We create this future, we call the slow function, pass value 1, and we ask for the value. So what happens here is like when it starts, there's a bit of overhead creating the future, a little bit more thing we don't benchmark now, and then the actual evaluation of slow 1 taking place. At the bottom here, you can see the lifespan of this, and the lifespan means from creating till we collect the value. So that's a very simple thing we can do now. We can also look at, of course, more than one. So here's an example where I use an lapply, and I call the slow function twice, and each time I create a future, and then I collect the values. So here we see 2 futures, And we say setting up the first, evaluating it. The second one can't create it until the first one is finished, because of course we're running sequentially. So that's what it looks like here. And in this case, the slow function is slower in this second value it takes, because it has to do other things. So what we care about is evaluation. That's really why we want to parallelize. We want to maximize this. We don't care about the overhead. We want to minimize the overhead. Profiling so we did a sequential one. Now look at the case. It's kind of silly, but if you set up one single background worker, we can do this like this, called a cluster and one single. So that now means that all the work is passed on to background worker. So here we see now it's creating a future. There's a bit of overhead now, and this overhead is a bit random. Comes out our garbage collection thing. But what's going on here is like it's first asking for finding a background worker, communicating with it, and then after it's finished launching, then the background worker is actually starting its evaluation. And at the end, it's gathering, there's a little bit of overhead on the background worker, and then the results are collected back to the main R session. You can't see this here, but there's like an event that we log called gather, which is very narrow, quickly collecting the results. But you can see now the future lifespan is we're creating it, overhead, launching it. And what about what happens when you call this is like the future function spends time here. And then the value function is waiting for the results to come back. So what about two futures? So we're running two futures still with a single background worker. Doing the same thing using lapply to create two futures. What we see here, first future created a bit of overhead to launch it, and then the worker down here starts processing future number one, and then the results come back. When it's launched our main R session can start creating the first one. So it's already creating the first one. But of course, if there's only one background worker, it has to wait for that to finish. So most of this time is waiting. But when the background is ready and done a little bit of cleanup, is ready to take on new data. And here is again a little bit of random startup, but then it starts calculating on slow here. So key here, we see the first future call in the lapply happens here. The other one happens here, and then it returns. And then we get to our value, which is waiting for results to come back from both futures. Okay, now the interesting thing, running in parallel. So doing the same thing now with two parallel workers. So with this now profiling data, we can see that it's creating a future, launching it, and you see here, this one was actually much faster than the previous one. Again, for this little randomness that R has. And as soon as it launched the first one, it can start creating the second one. And as before, actually. And then, but it can also launch it immediately because we have one more worker to send task to. So we have two parallel workers working on future 1 and 2, and they're almost running in parallel here. And here, then all this period after it's launched, the second one is waiting and checking in with the future. The two different workers, are you done? Can you give me the data? And collecting the data. Okay, so we heard from previous talks that there is overhead and data can be costly to send. So here's like an extreme case, an extreme in the sense relative to the speed of the slowness function. So here I'm exporting an 800 megabyte object. I call it huge. It's 100 million values, and each value takes 8 bytes, so it's 800 megs. So if I now pass that on to the slow function, that has to, of course, to be sent over to the worker also. So we're spending a lot of time here creating a future, and then launching takes a long time, and most of that time is to send the data over to the worker. And then the worker spends this much time, relative time to do the evaluation. When it sent over the first data and launched the first worker, it started doing on the second one. So now the main session is busy with sending to the second one. So that's why it can't really start collecting data from the first one until it's done communicating with the second one. So this is like a clear overhead and latency here. But then as soon as it's sent that over, it can collect the data from the first one back, and then quickly after it can collect it when the second one that finishes. So do we want to do this? Sometimes we do, because if you have a computer that can't handle, if this slow function requires a lot of memory to process, you might have to send it off to another computer that has bigger memory. So you have to pay this price maybe of sending over the data and let that other computer run it. So it could be people that want to do this, but most of the time we want to avoid this. So the balance between overhead and evaluation time is always important. Here's another problem, is like, if our function that we create, you don't have to necessarily send a lot of data, but you might get a lot of results back, like giant objects back. So here's a case where you get 800 megs returned. So it's very quick to create and launch the two futures, and they're very quick to finish. But as soon as they finish, it will take quite a while to receive the data back to the main R session. So that's another type of overhead. And with this framework, we can now not just guess and talk about it, we can measure it and optimize our code. So one goal here that come out here immediately, and that's been on the roadmap for a long time, is to start caching large global objects on parallel workers. And maybe then also having a centrally shared cache. And these are all data again. And this is by conservative design of the future framework, because you, as I mentioned, you as a developer should not have to worry about workers. Your code should look the same. And the reason why this is by design, all the workers are always wiping and cleaning up after themselves each time. So after the first one is finished, send off the data, it wipes its memory. Same with the second, it wipes it as soon as the data off. So when they get the new thing, there's no memory from that object from the past. But ideally, we want to do something like this, automatic caching, but it should also be optimized. So the first time you have to pay the overhead, but then we keep calling it, there should be minimal overhead, because this can be cached on the worker. And one way to do this is like, they have to communicate they actually have this exact same data. So there's all that the tedious thing that we're taken care of by the future framework internally. But also, how do we do it needs to wipe these big objects that it sent over at some point. But one way might be that if it calls another future and it doesn't use that big object, maybe then it clears the cache, or other ways having some kind of garbage collecting cache. So this is things that is in the works, and we can now profile all this with this new framework. Okay, that's my talk. I tried to make it a little bit longer because I had more time now. All the work here is available. There's a web page, and there you can find a link to the blog too, Futureverse. If I didn't say it, everything is on CRAN, this package and all other packages. There's a GitHub. The source code is on GitHub. There you also have discussions, and bug reporting is there. You can follow me on Twitter. I'm trying to post there too if you want updates. And the work has been in the past, several years ago, been sponsored by the R Consortium Infrastructure Steering Committee grant. And I should now advertise for that too. I'm actually now chair of the ISC, much later after I got this grant. And the ISC has twice a year you can apply for infrastructure related R work. So please go and apply for grants there. I am really excited too is that the future framework, I got the 2-year support from the Chan Zuckerberg initiative, the essential open source software. So it's allowed me to do this work not full time, but much more than on my spare time as I did in the past. So grateful for that too. Thank you, everyone. I'm open for questions, and I'm going to stop sharing.
Thank you, Henrik.
Which I didn't see. Did you guys see the result of the poll, or no? I have to click end. Sorry. Yep. Should I just summarize the poll for the community?
Yeah, go for it. And then we have one question in the Q&A.
Yep. We have, you can all see the results, I think. The first time I used this framework, but 20% of you are new to parallelization in this session. 60% done the basics. 15% are using parallelization on a regular basis, and 10% have a good understanding on the inner details about it. Most in this session, there's like Linux and Windows users, like 35-40%, Mac OS 20%. One user is like the 5% is on running the cloud, maybe RStudio Cloud. Interesting here, different from my tutorial. 80% are using RStudio as the main environment, and 20% using the terminal. There was a lot of people using other things in the tutorial I ran on Monday. Interesting, 40% of the people in this session have access to high-performance compute cluster, probably academia, and some people have access to ad hoc clusters in the cloud or local machines. But a fair bit of you don't have anything here, so you have your local machine to parallelize on. Okay, that was the summary, but that was interesting to see.
Yeah, quite interesting to see the demographics. We've got a question from Jose. It's been a few years since I've used the future package, but just wanted to confirm whether or not we need to define data frames, functions, packages when calling the future function.
So I'm going to guess what this means. Define data frames and function packages needed. That's probably like you have to explicitly declare what to send to the workers or the futures. And that's mostly automatic. There are corner cases because all that is done for static analysis of the code. And we can do a lot of their automatic. There are cases where it's not automatic, so then you have to guide the framework. Say, I need to use this. And one case is like data table. Sometimes you have to say, I am using data table here because it looks so similar to a data frame. So the static code can't tell it's a data table. But it's fully automatic most of the time.
And if I may ask a question as well. So you mentioned that in the future you'd like to cache the objects in some way. With respect to clearing the cache and what happens if like the user goes away and there's other users on the servers, do you think there's a way to handle that?
Oh, that's an interesting question. Yeah, it's that comes to like if you have shared machines, which a lot of us have, you don't want to have them sit idle. You want to have them being used, and you don't want to hog up slots or memory or sometimes even disk space that prevents other users from using the machine. So cleaning up after yourself is an important thing. It's a very complicated thing. I would say some kind of garbage collection. And that's anyone out there who can come up with a solution that works in general. I'm happy to hear. And this doesn't have to be implemented just in the future framework. This goes for everything. So, but it's a complicated problem, and also this is why this caching is not done right now. We just wipe to make sure everything is cleaned. But we can add these features in the background, and automatically all these packages already in CRAN will automatically get the benefit when we get that implementation, because the goal is that they don't have to change the code. And we've seen similar things in base R. It's like base R has been smarter and smarter and smarter, caching and just-in-time compilers, and we don't have to change anything. We just update R. So same philosophy here.
I have a question for you, Henrik. In terms of cloud environments, are there different issues that you have to, or you've thought about in terms of cloud or multi-cloud environments to realize this paradigm?
Well, so I don't use much cloud myself because I have access to big compute clusters. I think the most common thing here is like you use the cloud as a regular big Linux environment, and maybe spawn multiple machines with multiple cores on them. There is work, and we have regular meetings on this, trying to like automate this from Amazon Cloud, for instance. So you can sit on your local machine and spin things up locally, and it just works. But it's very complicated to set this up, so it's quite friction. What's your experience since you asked this question?
You know, it is a challenge, I think, especially if you want to have R engines be spawned in other environments, and to make sure that you have the proper connectivity and the impacts of data flow, as well as, you know, we've all talked about the expense of doing that. So it is an interesting problem, and I think it will be good to see how we can improve upon that going forward.
Yeah, I think it's a comment on that. I think there's a spectra. Where I'm trying to be a very general solution here. I'm trying to push that and learn. Every year we learn new things, how we can push it. The other one is like, I have a production pipeline, that now I want to optimize it so much, so it's super fast. That's when you can decide on a specific solution, like for instance, your solution, and let's optimize it. And I think most people start off, especially in academia, locally, on their local machine. It's like, oh, I actually have another machine in the office. Can I use that one? And then some people is like, okay, now we want to scale up like crazy. So now we start optimizing. And then you might not be able to use Future necessarily. You have to go your solution or Spark or something. But then you can maintain that for years, that environment. So it's a trade-off. Yeah.
All right, thank you, Henrik. There's a couple more questions, but I'm afraid we run out of time. If you wouldn't mind answering them on the Q&A directly.
Oh, okay.
But
Good.
Other than that, thank you very much to Mark, Puri, and Henrik. And I think it was a very interesting session.
Thank you all.
Hope everyone enjoys the rest of the conference.
Thank you. Same to you.
Same.